network theory. We call it circuit theory, whichever way you want. Okay. So what is asked, what is expected from you in this topic is basic KVL, KCL, star to delta, delta to star. So based on this, usually 1 or 2 marks they will ask. And then there is this steady state response. Transient response. You might need some theorems, Thevenin substitution. Theorems. Two-port. Last thing, there is this resonance thing. Usually for a second order system, there is a possibility of a resonance. So this is what is usually asked. I don't think anything that you discuss will go out of these topics. Okay. Obviously, if you know this good, very well, you can solve most of the circuit questions. I mean, it will be very helpful if you are studying this analog and anything else you are studying, it will be helpful. Okay. Ma? Locus diagram, electrical. Phase diagrams, we'll talk about it. It all comes here. Okay, so we have all that. We are going to discuss all these things. Locus diagram means it is about the phase, no? We'll talk about that phase here. In steady state response, we'll talk phase. All right. So before going into this, what I was thinking is, I will just introduce this. See, this is a subject about passive components, not active components. Active components, what is the definition of an active component? Okay, I don't know. But a proper definition of active component goes like this. It is usually a kind of a two-port system, at least two-port, I could say, where the flow of this energy is controlled by this side. That is what we call active, otherwise passive. So active means where the flow of one energy is controlled actively by other side. I want you to make good notes. Okay? Whatever I say, you just make good notes. Sometimes I'll consciously say make a note. Otherwise, you should be very careful in making good notes. So active means usually the proper definition goes like this: that there is active control of the flow of the energy of one side by the other side. That's when we call it active. There is not an exact bookish statement, but the idea goes like this. It's like a water tap. That's what you should have in mind. That's active component. So this subject, I think we are going to deal all with most cases passive components only, where there is no active control and all. It just does what it does. I talk about it, but we will talk more of passive components and passive network analysis. Active network analysis will do it in analog. Okay, the components of active, which what is the examples of active components? Lemma, active example be transistors, op amp. So these things we call as active. So here we are going to talk about only passive components. I am more interested in resistor to start with. We'll introduce the basic math equations behind it. Basic math equation, as you all know, V is equal to I into R. I can be written as dq by dt. So this can become, this will be R dq by dt. From a charge viewpoint, this is a first order equation, first order differential equation. From a charge viewpoint, this is a first order differential equation. Network theory class. From a charge viewpoint, this is a first order equation. You can see dq, d by dt is there. This is about the resistor. See, we just started with the resistor. And the next I would like to talk about capacitor. What is the equation here? Very good. Q equal to CV up, Q equal to CV. So you could say I equal to dq by dt, or you can say I equal to, C is a constant, something to do with the geometry. So the constant comes out, it is C dV by dt. Or if you are only looking at V and Q, see, how did I say it's a first order equation? On what basis? I was interested in only two things. That is, use another color. V and Q. When you look at the relation between the V and Q, this is a first order equation. When you look at the V and Q, what can you say here? Is it a differential equation at all? No. So we can, in other words, say it is a zero order differential equation. That is, there is no differentiation at all. So it's a zero order differential equation. This order is all I am trying to make, not with V and I, but I am trying to make it with V and Q. That's what you should be very careful. V and Q. And then comes inductor. What can you say about inductor?
V equal to L dI by dt.
Correct. Inductor. L di by dt. If I say I equal to dq by dt, then what will it become? L d by dt of dq by dt. So on this will be V equal to L d square by dt square and Q. What will be this called? This is a second order differential equation. So we started with a simple resistor. That's today's class. We started with simple resistor. We see that resistor's basic governing equation, that is the relation between V and I, is V is equal to I into R. We call it Ohm's law. And then we kind of substitute I equal to dq by dt. We try to draw the relation between V and Q. We say it's a first order differential equation. When you look at the similar way for a capacitor, it's a zero order differential equation. And for an inductor, it is a second order equation. Does it matter? How does it matter? Why do we talk about this differential equations? How does it matter? That's the next question. How does it matter? I want to say a few things. We'll go one after the other. They're all okay. I think before going into that, I want to talk about this. This is a time domain equation, right? These are all time domain equation. How does a frequency domain equation look like?
Yes.
Frequency means yes. None. S is a Laplace transform. For frequency domain, which transform do we do? Fourier. Fourier transform. Fourier transform pushes into Fourier. I mean frequency domain. Actually, Fourier is a special case of a Laplace transform. When you say S equal to j omega, it becomes Fourier transform. So now we have made time domain differential equations. Next, I am going to push it into frequency domain equations. I am not interested in Q anymore. I will try to keep it in V and I relations. If you try to do, maybe I will write it here only. There is some space. So my next intention is, how do you write the frequency domain equations? We have been writing time domain, frequency domain, because frequency domain gives us a lot of picture. That is why you are studying a subject called signal cell system. You are just trying to push everything into frequency domain. So here there is no differential equation at all. So for resistor, I'm only interested in V and I relation. So it looks like time domain, frequency domain, all the same. But when it comes to for a capacitor, when you try to push this equation into frequency domain, instead of d by dt, you will put S and S equal to j omega. So it will be I equal to C j omega V. And how about here for an inductor? L j omega. So these are all frequency domain equations. We have made time domain equations, and these are all frequency domain equations. I'm going to stop here for a few minutes. First point to note, I say resistor is a first order differential equation, not based on V and I relation, but because of V and Q relations. And the next I try to push the time domain equations into a frequency domain. And now I'm not interested in Q at all. I'm only interested in V and I. So you should be very careful. I'm only interested in Q only when you talk about this kind of systems. Why do I say, why am I interested in Q, why this kind of system? I'll come back to it a little later. For now, I just want you to understand, I'm interested in this forms of equation when you're trying to push it into frequency domain, this green color ones. So there are two differential equations. One is I and V, and the other is V and Q. So this is where we started. We just introduced resistor, capacitor, and inductor. If you have come late, you can take a picture. Okay. Now, when can you take frequency transform, sir? Any transform. We said transform, right? Fourier transform, Laplace transform. When can you take a transform? Can I take a transform of a nonlinear systems? Can I take a transform of time invariant systems? When can you take a transform? Very basic question. You study signals and systems. What do you study? All you study is Z transform, S transform, that is Laplace Z Fourier transform. When can you take, before studying that, you will study a subject called LTI systems. What is the purpose of LTI systems? Only if you know it is a LTI system, you can take a transform smoothly. If it is not LTI, say for example, a linear time varying systems, you have to do some jugaad and then you can do a little bit transform, but still a proper LTI system means you can take transform easily. Why are we interested in transforms? When you take a transform, you get a easy picture of the system. For example, if you take a Fourier transform, now we have taken a Fourier transform. I'll show you a simple picture why we take Fourier transform. If you try to say, I'm keeping my frequency constant, when your frequency is constant, say an AC source, and I put an impedance here, let us say the impedance is just R. When I increase the voltage, what happens to the current? If it is just a resistor, if the voltage increases, current increases. What is the governing equation? V is equal to I into R. So I say the relation, my graph will look like this. That is, when I increase the voltage positively, my current will increase positively. When I increase the voltage negatively, current will increase negatively. Now, if the resistance is, that is, it is inductor XL. XL means it is V by I. V by I is called impedance. So XL, which is LJ omega. Now, what can you say about V and I relations for an inductor? When V increases, what happens when the frequency is constant? When the frequency is constant, V and I are related by V by I is what? I'm interested only in the magnitude. Say it will be L, because omega is constant. Let us say proportionality. L is also a constant. So V and I will be directly proportional. So my graph will look like this. If I do something like that for an capacitor, this is for an inductor. XC is V by I 1 by JC omega. And if you say frequency is constant again, so this fellow is constant, let us say 50 hertz. So it's a constant number. Capacitance value is, let us say, 1 microfarad. That is also constant. So V is directly proportional to I. So whenever V increases, I will also increase. So you're going to get a straight line like this. When you push the equation into Fourier, that is frequency domain, I get a easy equation. If it is, since it is not d, if it would have been d by dt, it would be very difficult to handle. Now it is just a j omega, and I say the omega is constant. Immediately I get a picture relation between V and I, and it is a straight line. Whenever a graph is a straight line, you can say the system is linear. I'm just trying to explain that the system is, all these three are linear components. That is RLC. All are linear components. How do I say? I say the relation between V and I. I say that they're all linear components. Graphs are all straight line. If it is not a straight line, it's a non-linear system. We are only talking about linear systems. At undergraduate level, only linear systems. So where did we start? We started with a simple RLC component. From RLC component, we gave equations: frequency domain equation, time domain equation. We are interested in frequency domain because it gives a easy picture of a system. What do I mean by easy picture? Like this. I was just trying to understand that this is a linear system. For that, I need a graph relation between V and I. If it's a differential equation, it's difficult to get a graph. But if you try to push it into a frequency domain, it's much easier to get a graph. The relation, I mean. You can call this as a transfer function. In a control system, you say this is a transfer function. Here we usually say gain equation. Output by input is a gain. So for people who came late, we started here. We started with a simple understanding of resistor, capacitor and inductor. What is the relation between them, V and I and V and Q? Based on this V and Q, we say what kind of a differential equation it is. First order system, second order system, third order system. We usually don't use V and I relation for this. This is based on V and Q because Q is more fundamental. I is not fundamental. I is kind of a derived stuff. Next stage. All right. I'll just give a brief idea about what is a zero order system, first order, second order, and then we'll move into the next. What kind of a response do you get for a zero order system? Let me say the input is something like this. The white color is the input. Say I give an input like this. This is the input signal to the zero order system. It can be anything, zero order. What kind of output do you expect for a zero order system? Let me do that for first and second. Why are we interested in this word zero order, first order, second order? I just want to give a brief picture, then we'll go into the subject. White color is the input. I'm giving some kind of a step input. What kind of responses do you think you can expect? In a zero order system, what will be the response? Sir? No. It will be exact match of input. Whatever you give as an input, exactly the same you will get as the output. Yellow color is the output. You're going to get exactly same. Zero order system. And how about first order system? I'm not teaching control system. I'm just giving you a picture of what is the meaning of the zero order, first order, second order. For a first order system, how will be the output?
Yeah, straight line.
No. Correct. It will go something like this. And it will reach the output at the infinity. So it will be a slow rise. We usually say this is some exponential rise. Exponential rise. What is that exponents? We are going to talk. And how about a second order system?
Oscillate above the input and it will settle down.
Okay, that is one possibility. It can go something like this and then settle. Is that the only possibility? Very good. There are multiple possibilities in a second order system. In one case, it can be like this. In the other case, it can be an undamped sine wave, continuously oscillating. And the other case, it can be somewhat similar to the first order. We say over damped or critically damped. Both will look somewhat like this. And then in another case, you can have exponentially increasing, totally unstable system, unstable system. So in a second order system, multiple things are possible. We call this as underdamped, 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 and this is undamped, and this is it can be critically damped or over damped, whatever. And this is unstable. So there are usually multiple possibilities. So it's not that there's only one possibility. The way the system is, you can have multiple possibilities. So how does it matter to have a zero order system? A zero order system means whatever you give, it just happens again. Instantly, no delay, it just happens instantly. There is no delay at all. We call it dead time. There's no dead time. It just happens instantly. If it's a first order system, most cases it's exponential rise. Unless and until you make a negative resistance and amplify, it can be exponential rise and stable. So I'm not going to talk about that beyond the scope of this. And in second order system, you can have multiple possibilities, which is more exactly you need to know as a part of a undergrad student, that there are multiple possibilities: underdamped, undamped, critically damped, unstable systems. Now, out of this, which one you will call it as an oscillator? Undamped is a oscillator. So maybe you should make a note. Undamped system is also called an oscillator. So if you are trying to design an oscillator, which order system is it? Well done. So you're not going to design a zero order or first order. You need a second order system. And a small important warning, all we are doing here is, what is this axis? Time. So we are all talking about time domain. I'm not talking about frequency domain yet. I'm only talking about time domain. So again, a small bird's eye view picture. I started with saying this is the syllabus for the subject, and in this I wanted to start with KVL, KCL. So to start with that, I need to know a basic understanding of these components: resistor, capacitor, and inductor. I said all these three are linear components. So what we are doing is a linear differential equation analysis. That's all we are going to do in all this subject. And in that, you could have a first order differential equation, second order, third order, whatever. And as a part of the subject, transient response means a time domain analysis. Steady state response means frequency domain analysis. So basically, this subject is designed in the way you are doing time domain analysis and frequency domain analysis. That's what this subject is all about. Okay. And this resonance, you can say it's more of a frequency domain analysis. These are all theorems and things like that. So effectively, you need to know what is time domain analysis, what is frequency domain analysis. If you know that well, you are good enough as an electrical student. This is what is expected from you. When do you use time domain analysis? When do you use frequency? If they are talking about time domain, when do you use time domain analysis? When do you use time domain analysis? If they are talking about what is the time at which this one becomes 63.1% of this? For example, this is 10 volts, this is 6.3. When does it become? What is this time? Then you will have to do time domain analysis. I'm just giving you an idea when to do time domain analysis. Okay. So this is a usual question. I've seen every year there is a question on this. For a first order system, we call this as a time constant. So this parameter is called time constant. For a first order system, there is only one parameter they are more interested in, which is called the time constant. Now tell me, what is a zero order system? What component will be there in the zero order system? Out of RLC, what are the three components we said? Which is a zero order system? Capacitor. So if they are talking about zero order system, that has only capacitor, only capacitor. If it is they're talking about first order system, what should be there? Do you think I can use capacitors and only capacitor? If I build with capacitor, do you think I can get a first order system? No, you need a resistor and capacitor. So it's usually an RC circuit. From a viewpoint of a voltage source, viewpoint, and RL circuit will also be a first order circuit, but from a viewpoint of a current source. Just make a note. As class goes along, you will get an idea what I mean. So an RL circuit and RC circuit. If they have a current source and an RL circuit, it is still a first order system. And for a second order circuit, what is a good example? RLC. Do you think I need definitely an inductor to build a second order system? Without inductor, just say I have only RC. Do you think I can build a second order system with it? You understand the question, sir? I say RC is a first order system. If I multiply two RC, just I cascade two RC circuits. Now you are multiplying two differential equations. Two first order differential equations, if you multiply, it will become a second order differential equation. So it's not that every time you need an inductor. I can put one RC like this and again one more RC like this. Now this is a second order. So you can still have a second order system without an inductor. Effectively what I am doing is I am multiplying two first order differential equations. You end up getting a second order differential equation. So you can still have a second order system without an inductor. I am just giving a picture of this second order. Now, why did I say this? Now you go back and see Wien bridge oscillator, RC oscillator. Do you see inductor there? But still it is a second order system because it's an oscillator. An oscillator should be a second order system. You see only R and C circuits there, right? So you can still build a second order system with RC only, not necessarily two RCs. You can have multiple RCs and make sure that it's a second order system. So you can still build a second order system for oscillator or whatever purpose you have. Tuned amplifiers there also. All right. So we just started with RLC. I've been talking a lot about them. A basic understanding of capacitor, I think it's worth giving. How do you understand a capacitor? Uh, how do you build a capacitor? What is a capacitor? Very good. Two conducting plates separated by a dielectric. I don't want to make it more of a EM class, but still, we just want to say that there is something here called dielectric, which has an epsilon R. So, if I give a say I have a switch here, I close it, I give 5 volts. Let us say the capacitor is 1 microfarad. If I close it, what will happen? This is a DC source, constant DC source, 5 volts. If I close this switch, what do you think will happen? Charges will flow and go and sit on this. I will use different color, yellow color. Plus here, minus here. To be more specific, I'll just give you a small idea. I just can't resist giving it. This dielectric will develop some charges this side. We call it bound charges. These are all bound charges. And the charges I put from the source, we call it free charges. So actually there are two charges here. One is you put free charges, that is from the source, and that will polarize this unit, and then this will have some charges here, which will not flow, but it will still have a charge. We call it bound charges. But leave that apart. We can talk it later, which is called polarization. What makes this dielectric material different from an insulator? Okay, leave that. Now, if you turn it on, all these charges will go on sit. With what speed? That's the question. With what speed? Does it take some time to charge? My question is, does it take some time to charge? Yes, no. No. I said capacitor is a zero order system. The moment you give, instantly it charges. There is no time taken at all because this is zero order system. இந்த வயர்ல ரெசிஸ்டன்ஸ் இருக்கு நான் சொல்லவே இல்லை அப்படின்னா there is no resistance. That means infinite current can go. நான் ஆன் பண்ண உடனே infinite current போய் immediate charge ஆயிடும் because capacitor is a zero order system. So if you try to plot voltage on a capacitor, the moment you turned it on, that moment only I got 5 volts. That moment only I got 5 volts. Now this is a voltage. So because capacitor is a zero order system. See how it matters. If it is zero order system, it takes no time to work. It just happens instantly. Now this is about a voltage. What can you say about a current? Can you plot a current graph? After it charges to 5 volts, do you think there is some current going? There is no potential difference. So current will not go. So can you plot this current graph? How does it look like? When you turn on a switch, how much current is going?
Exponentially decreasing.
So exponentially decreasing. Say for example, here it is 5 volts, right? Here the voltage on the capacitor is 5 volts. Here also 5, here also 5. So current here will be 0. So after this instant, every time 0. Do you think there is no current at all? No. First, understanding what happens to the voltage. There is no resistance at all, there is only a capacitor. What happens? When you push the switch, there is nobody to resist the flow of current, so infinite current will flow. For how long? Only for that moment. That is this instant. And only for that instant, infinite current will flow. After that, no current. Before that, no current. This is practically. I should explain it mathematically, right? What is I? dV by dt. What does a different? When you differentiate this, you should get this. When you differentiate a voltage graph, you should get this. When you differentiate constant, it is 0. There is only change here. Only during that change you will get impulse. This is the answer. What is a capacitor? A capacitor is a zero order system. So that means it doesn't take the relation between V and C is V equal to A by C. So it's a zero order system. I see there is no need for capacitor to delay anything. Whatever you do, you give as an input, instantly the output will appear. Now, if you connect a current source, what will happen? Next is when you correct a current source, what will happen? A constant current source, let us say 1 amps. 1 amps current source is connected to a capacitor which is 1 microfarad. Tell me what is the voltage graph? This is time V. I had a voltage source, now it's a current source. Again, don't think there is a governing equation. What is the governing equation? I equal to C dV by dt, but I want V equal to. If you wanted to make it V equal to, what will it be? V equal to? Yes. It's an integral equation, right? So what is it? V equal to 1 by C integral I dt. So use this equation. Tell me what will happen here. I am closing the switch. Let us say there is a switch. I am closing the switch when t equal to 0. There is no resistor, only capacitor. So I just took the governing equation of the capacitor. What is I? I equal to 1 amps. So you can just put I equal to 1 amps there. Capacitor is 1 microfarad. So you can put it there. Tell me what is the voltage. Maybe I should ask like this. What is the voltage at t equal to 0? What is the voltage at t equal to 0? What is the voltage at t equal to 1 second? What is the voltage at t equal to 2 seconds? Tell me like that. Linearly increasing. So can you tell me the numbers? How do you make this equation? What will this integral will be? What will be the limits of the integral? Switch is closed at t equal to 0. What is the limits? 0 to t. Which time you are interested in? Which time you are interested? So if you say V equal to 1 by 1 microfarad, you know micro means 10 power minus 6, you know how to handle it. 0 to t, 1 amps, it's again a constant, it comes out dt. So it will eventually become 10 power 6 If you integrate 0 to t dt, it will be t. So this is the equation you have got. When you say t equal to 1, it will be how much volts will it be? 10 power 6 volts. And 2 means it will be 2 times 10 power 6. So the voltage will be straight line. I have not drawn it properly. It's a straight line. It's a straight line. Okay. So when you give a constant current source, voltage here will be linearly increasing. Linearly increasing. And if I ask you what will be the current graph, I think I'm just asking you the obvious thing, but still you should be able to say. What will be the current graph? What is the current through this? Say I put an ammeter here. What will be the current flowing here after you turn on the switch? How much current will go? So it's just 1 amps, right? That's the source. So from this instant, it will be step 1 amps. So what did I do? I just started with a simple capacitor. I introduced it. I connected a voltage source. I turned on the switch. I connected a current source. I turned on the switch. I'll just do one more, then we'll move on for an inductor. So I have a current source, 1 Henry of inductor, 1 amps is there. What can you say about the voltage graph? What is V? What is the governing equation for this again? V is L di by dt, right? But I want the integral thing. Or maybe I'll put current source. If you give a current source, what will be the, I want current here then. What is current equation? 1 by L integral P dt. So if it's a constant voltage, the voltage will come out, then you will end up getting V by L into T. So let us say this is 10 volts, 1 Henry. So this will be 10 times T. What will be the current through the inductor? What will be the current through the inductor? As I turn on the switch, 0, 1, 2, 1 second, 2 second, 3 second. What will be the current through the inductor?
10.
Current will be 0, and then I'll use a different color. So here it will be 10 amps, and here it will be 20 amps. Of course, voltage will be a straight line. So what is happening in an inductor? As you turn on the switch, how do you explain an inductor? Again, some bit of Lenz's law and all required. I don't want to make it a EMT class. But whenever there is a change, it resists, which is the Lenz's law. Lenz's law states, whenever there is a change, the system resists. Just remember that. Now when you turn on the switch, immediately when you give 10 volts, what this inductor says is, no, I've been in no current mode for so long, suddenly you are giving me current, I'm going to resist. And that resistance will change slowly. Only this much I'll talk now. Later in different class we'll talk about it more. I just want you to at least understand that the graph for an inductor for a voltage source looks somewhat like. What is the underlying principles for an inductor? You just have to remember this Lenz's law. System opposes the change. That is where inductor starts. Self-inductance. We'll talk about it in EMT class. A different time, different class. All right. Is there anything else to say? What happens if you give constant current source? You want me to do it? Constant current source for an inductor.
So it will be 0 volts.
Why 0 volt?
L dI by dt. So the change in current will not be changing current.
What is the voltage? V is equal to L di by dt. As I was saying, Lenz's law says it opposes the change. If there is no change, there is no opposition, right? Because there is a constant current source. For a constant current source, there is no change. The AC current source, it's a different ball game. Since it's a constant current source, there is no opposition. So the voltage will be 0. So that means this is just like a wire. It offers no impedance to the system. It just allows, it's just a wire. It's just a wire. Okay, there is nothing happening there. Maybe the moment you push the switch, there might be something, but afterwards there is nothing happening there. We'll talk about it more. For now, I just don't want to push too much into it. Where did we start? Again, a bird's eye view picture. Okay. Basic differential equations. Here we did not write the integral equation. What is the integral equation? We used it some time back. What is the integral equation? V equal to 1 by C integral 0 to t I dt. And how about here? The integral equation is I equal to 1 by L 0 to t. These are all integral time domain equations. There is something called integral frequency domain equation. I am not doing it again. I just wrote differential frequency domain equations. So when did we use this? Whenever you talk about current as a source. When do we use this? Whenever you talk about voltages. So this is the cause, this is the effect. Whatever you, in any mathematical equation, whatever you write on the right side, we call it source. Left side is the effect. So after this, we just said all these three components are all linear. RLC, all these three are linear components. And then we just gave introduction for a zero order system, first order system, second order system. What kind of responses, time responses you could expect. We call it transient responses. And then a bit of introduction for this transient response for a capacitor with voltage source, current source, inductor with voltage source, current source. That's all I did. Okay. What is your understanding about KCL? Kirchhoff's current law. What does it say? If you can make it as a statement. Sum of all the currents entering the node equal to, you can say leaving, or you can say, yeah, that's also one. Sum of all the currents entering the node equal to 0. That is something that I remember, so I would like to say it that way. But as you say, you can always say that all the currents entering the node is also equal to all the currents leaving the node. What is the fundamental, where is this coming from? Where is this? No, it actually, the whole of the circuit theory comes from field theory. In field theory, there is something called continuity equation. Continuity equation. You go back, look into it. That from that continuity equation only KCL comes. I'll just make a note here. KCL comes from continuity equation, which is in the field theory. If you open any Maxwell's book or any field theory book, you'll see something called continuity equation, del dot J equal to d rho by dt. I think minus is there, somewhat like this. And okay, so it comes from this. All the currents entering the node equal to 0. Let us say this is I1, I2, I3, I4. You can say I1 plus I2 plus I3 plus I4 equal to 0. You can have any number of branches. You just have to add all of them coming in. If you define it like this, just like this. We could do some simple problems just as a part of the exercise. That is, I'll take this only. Maybe I'll just add some voltages. One volt, 1 ohm, 2 volt, 2 ohms, 3 volt, 3 ohms, 4 volt, 4 ohms. Let us say, give some name here, Vx. Can you write KCL at node Vx? KCL at node Vex and find Vx. The question is find Vx. The moment you see this, you should be writing KCL to find Vx. Can you write a KCL at node Vx? You can write KCL, most of the necessary learning you need for this exam is over. KCL is the workhorse. KCL can solve most of the problems. How do you write KCL? What is I1 here? What is I1? How do you define I1? What is I1? Sir, always you say, I think if you're trying to say like this, yeah, you can say Vx minus 1 volt divided by resistor. So you can say like this, Vx minus 1 volt divided by 1 ohms is I1. This is I1. This node minus this node voltage divided by the resistance is this current. What is the current in this branch? The potential difference across this component divided by the resistor. Continue writing it like that. Equate it to 0. Tell me what is Vx. What is I2? I2 is Vx minus 2 divided by 2. Keep writing it and then tell me what is the final value of Vx. here Vx minus 2 divided by 2 plus Vx minus 3 divided by 3 plus Vx minus 4 divided by 4. What is Vx? So at the end of KCL, what are you trying to find? Most cases you are trying to find the voltage at that node. Most cases you are trying to find voltage at the unknown node. So KCL will give you a simple way to find the voltage at a node, unknown node. We don't know the voltage, that's what we are trying to find. Most cases KCL is used for this. Some cases you know these three currents. If I say this is 1, 2, 3, you can always say that this is 3 plus 2 plus 1, which is 6 amps. All right. So what is the answer here for this?
48.
What is the number, sir? Final number. Sir? 1.9 volts. So the one of the application is KCL is finding the voltage at the unknown node. This node I don't know the voltage. I use KCL, I get the voltage. We're going to see lots of such applications of KCL in op amp, particularly when you study analog. You'll see that in op amp this is more very often used. KCL.
Can we also say that KCL comes from law of conservation of charges?
Yes, sir. Law of conservation of charges is what leads to continuity equation. From that only we will end to this one. Law of conservation. See, I'll tell you this continuity equation. J is the current density. Rho is the charge density. If there is no charge in this area, there is no charge escaping this region. That means whatever comes in has to go out. That is the meaning of it, which is comes from law of conservation of energy, charges. Law of conservation of charges. If you see that first page is law of conservation of charges, the next page is continuity equation. All right, so this is one application of KCL. I can give you another application. Let us say I don't know the voltage, but I know the currents. If I say this is 1 amps, this is 2 amps, this is 3 amps, what is this current? Minus. So you can see that whatever comes has to go out. Since the direction I put it like this, it has to be minus 6 amps. So this is one other application of KCL where you try to find the unknown current in a branch, given that I know all the currents in the other branches. So okay, these are all some basic stuff, kid stuff, you would have done it in your school days. Next is KVL. What is a KVL? Say I have a kind of a loop situation, mesh loop situation, and in that loop, if I say this is 10 volts, 2 ohms, 8 ohms. In this case, what will you apply? You don't need KCL. You can apply KCL still, but yeah, Ohm's law is the basic law, but KVL you can apply. What does a KVL say? Sum of all the potential drop. 0. Very good. So you can say that here it is sum of all potential equal to 0. This one, where does it come from? From field theory, it comes from something called E field, a conservative E field. A conservative E field, del cross E, the curl of the electric field is 0, which leads to the potentials being all the summation of all the potentials being 0. So here, how do you say potential equation? How do you write it? Current entering the node, current entering the component, leaving the component. Whenever current enters, you say plus. Whenever it leaves current, minus. So the 10 volts So from here, when you go like this, when you're traveling like this, you see there is a rise in potential. So I will say plus 10 volts. And the next case is there is a drop in the potential. So minus, I don't know the current value, but I into R is 2 ohms. Again, there is a drop in potential. So it is I into 8 ohms equal to 0. This is KVL. When you write a KVL, the first important thing is you should mark the direction of the current and you should give the potential values, where it will be plus, where it will be minus. For all the sources, it will be already mentioned, so you don't have to worry about that. But about the load, current entering side is plus, current leaving side is minus. That's the important key part there. Once you know that, you can always write. So what will be the current value here? 1 amp. Can you use KCL and solve this? Where do you use KCL? I ask you to, which node? If you are planning to use KCL for this, one way I would suggest is you can use KCL at this node. Can you write a KCL at this node? Vx. Write KCL. I want to solve the same circuit with KCL. What is the how many branches are there in it? 2 branches. This is just a wire length. Leave it. There are only 2 branches. So for 2 branches, you'll have to write KCL. I1 plus I2 equal to 0. So how will you write it? Vx minus 10 volts divided by 2 plus Vx minus 0 divided by 8. You can write it, please do it. I just want to show you that how KCL is beneficial. Vx minus 10 divided by 2 plus Vx minus 0, because it's 0 volt here, reference volt, 8 equal to 0. From this you can find Vx. I just want to show that KCL is bigger than KVL. So what will be the voltage there? 8 volts. Can you solve the left top? That with KVL? This one, do you think you can solve it with KVL? There's no loop. If there is no loop, can you solve it? No. You see how KCL is bigger than KVL. You can use KCL anywhere. KVL has some limitations. So from Vx you can find everything else you need. Basic KCL, basic KVL. The one thing we should be talking about, something called star delta. You all know it. Nothing great. Some basic math stuff. Delta to star, and then I'll do star to delta. A very useful tool. So if you want to convert Yeah, delta to star, the equations go like this. Star to delta. All right. I could see a question here. See if we can solve it. This is kind of old gate question around 2000s. 5, 30, 15 ohms. What will this be? These three resistances can you find?
I think it's a direct substitution of formulas. You can substitute. Delta to star. Delta is given. What they are asking is star. What are the answers? 3 resistance values. Yes, sir. 3, 1.5 and 9. So the resistances are 3, 1.5, 9. There is the option. See if everybody gets it. Basic substitution. See, this one was asked a little later, 2001. What is the option, sir?
Yeah.
Yeah. Option A. Everybody gets the basic stuff again. See, simply speaking, one thing that I remember that these values are the star values are smaller than star values are smaller than delta. So this is something that I remember. Solve some more, but let me see if there is something worth was solved. I could see this question. Let us see if we can solve it. See, this is again 2001, an old question. What is the voltage here? That is the question. Think about it. Which one will you use? KVL, KCL? You just need voltage at the unknown, right? So you can use. See, we did something like that some time back. We were interested in this voltage. What did we use? KCL we used. So you can do something like that there, but let us see if it works. See, if you have to use KCL, what does the KCL say? You are trying to find voltage, right? I mean, sorry, you are trying to write an equation. This white color. How will you write a nodal equation for this one? Let us say Vx. What will be? You have to give name here. This one I know, 12 volts. What is this voltage? I don't know. So let us say Vy. So you'll be stuck with this. How will you write KCL for this? Let us just at the sake of completion. Vx minus 12 divided by plus Vx minus 0, because this branch is there, no? Vx minus 0 divided by 4 plus Vx minus Vy by 2 equal to 0. So again, this is a two variable, single equation is not sufficient. You need another equation. Now, right, this is KCL at Vx. Can we write KCL at Vy? What will be KCL at Vy? Vy minus Vx divided by 2 plus Vx minus Vy minus 0 divided by 2 equal to 0. So you've got two equations, two variables you can solve. This is one way. You can write two loop equations. I'm going to do that also. Of course, you don't need all these things. You can just reduce the resistances, find the current. You can do it. I'm just giving you an idea that you can do all these things. How to write these equations? See, for a simpler problem, you don't need these equations. You can just reduce all the resistances, make it a single resistance, find the current, divide the current, it's done. I just took this opportunity to write this KCL thing. How do you write KVL? Two loops, loop equal.
First loop,
Yes, sir. How does it look like? Say I'm going to write this KVL thing. Four, four, two, two. How do you write KVL? You have to give current names, right? There we give node names. Here, what will be the current names? I1, I2. So, what will be the first loop equation? 12 minus 4I1 minus 4 into I1 minus equal to 0. This is for this loop. And how about the second loop? You can start with this component. So current entering side, leaving side. So you can say minus 2I2, minus 2I2, another minus 2I2. Yes. And how about this one? Minus 4, I2 minus I1 equal to. So you can solve this and then find I1 and I2. How to write KVL equations? How to write KCL equations? Again, two variables, two equations. You can solve them. You can get basic fundamental stuff. There is nothing new we are discussing. Why don't you go ahead solve these two equations? Reduce these equations and then solve. At least not solve, at least reduce them into I1 and I2. This will become 12 equal to 8 I1 minus 4 I2. 0 equal to 8 I2. So you get two equations. When you get two equations, two variables, you know how to solve. I'm not doing that. I just want to give you an idea that you can do something like this. Now you don't have to do all these things. In this particular problem, is much easier to solve. What do you do? Reduce these resistances. How do you reduce these resistances? Yes. 4, 4, and these two are series. When you have series resistance, what do you do? It will become 4. When you have 2, 4, it will become 2. How do you do parallel resistances? 1 by R equal to 1 by 4 plus 4. You can do that reduction thing and then you end up getting now what is the current here? Six ohms, 12 volts. So what will be the current? Current will be 2 amps. And what we understand is from the source 2 amps current is starting. and it has to divide between these two same branch resistances. So it will be equal division. So it will be 1 amps here, 1 amps here. And in that case, what is the potential here? 4 volts. So the answer is 4 volts. 2 amps is coming from here, and then you start understanding that it divides between two same resistances. So 1 amps into 4 ohms, it will be 4 volts. So the answer is 4. You don't need KVL, KCL all the time, but in many cases you will. The same problem we tried to solve with KCL. We had two variables, two equations. And the next case we tried to solve it with KVL, two variables, two equations. And then we see here there is a small opportunity that I can reduce it into a single resistance. If you can reduce all the resistances to a single one, then you can always find the current, and then there is this current division thing. From that you can find the voltage. Right? Something very basic we will discuss. Current division. Say 2 amps is coming from here, like the previous problem. Two resistance branches are there. If it is same resistance, you know how to find. I'm going to give you a different resistances. How does the current divide? On what basis?
Ratio.
Where will be more current? Where will be more ohms? Through this one or through this one? More current. How much more? Is there some simple yes? How much more current? 2 amps is coming. Through which resistance more current will flow? 1 ohms. The next is how much current will flow here?
Sir, 1 by 3 into 200.
1 by
3 into 200.
1 by 3 into 2 amps. Okay, if I say it is 1 by 3 into 2, how much is it? 2 by 3. Here, how much will it be? If you say it is 2 by 3 into 2, how much will it be? I made a small mistake. See, so actually it should have been
2 by 3.
So the current through this one, maybe I'll use a different color. It will be 2 this resistance divided by resistance. How much will it be? And here it will be this resistance so it will be 2 by 3 amps, and this will be 4 by 3 amps. When you add them both, what should you get? 2 amps. So the basic thing you all know, there's nothing new I am teaching. What I am trying to say is the current through this resistance is decided by this one. The current through this resistance is decided by this one. 2 by total resistance into the current. A very basic idea, but an useful tool. Current division. So if the resistance here is greater, current through this is greater. If the resistance here is lesser, then the current through this is lesser. Current division. By the way, for the same problem, how will the voltage divide? Let us say here it is 10 volts. Here I said 10 volts. How will the voltage divide?
Sorry, it will be on the same 1 by 3 into 10.
Voltage across the junctions are always
Same.
same. So what will be the current here then?
Current will be varying, sir.
How much will it be? Tell me the number.
2 by 3 into 10 volt.
If you have 10 volts here, here also it will be 10 volts. Again, nothing great, something all you all know it for so long time. So what will be the current here? Voltage of the junctions are same. The current will be 10 amps. Here the current will be 5 amps. Does this resistor matter when you are trying to find this current? Do you think of this resistance at all to find this current? Yes, no. You understand the question? When you talk here, this resistance mattered to find this current. Here, does this resistor matter to find this current? No. Now, what does that tell you about a current source? Sorry, voltage source. Is same.
And dependent on that resistance.
That is, a voltage source can give any amount of current you ask for. To maintain the voltage, 10 volts. If this fellow asks for 5 amps, it will give. If this fellow asks for 10 amps, it will give. Say I short it here. That means it is asking for how much current? Infinite current. It will still give. The idea of voltage source is actually this. I want to be more. So any amount of current you ask for, a voltage source will give, and it will try to maintain the voltage, constant voltage. Right? Now we come for series, this parallel resistance thing. How about a series resistance thing? I give here 10 volts, 1 ohm, 2 ohms. Now I ask you, what is the voltage across this? What can you say? How do you go about it? Where the voltage is high? Across 2 ohms. So that means who decides that voltage? I mean, the particular resistor or the opposite resistor? See, in this case, the current through this is decided by opposite. But in this case, the voltage is decided by particular resistor. So the what will be the voltage here? 2 divided by total resistance into 10. How much is it? 20 by 3. I'll leave it that way. And how about here? 1 divided by 3 into 10. 10 by 3. I want you to appreciate the difference between current division and voltage division. In voltage division, we only talk about that particular resistor. In a current division case, we talk about the other film. All right. How about the current thing? I mean, I give a current, constant current source. What is the voltage here? What is the voltage here? Here it will be. Here it will be. On what basis you decided? Current into resistance. Oh. Current into resistance. Something very basic, sir. Nothing great. I just wanted to talk about voltage source and current source for a two parallel resistances or maybe series resistances. Make a good note of it. It will save a lot of time as we go along. See, what I see is a usual mistake. I see people doing it, which is very important. I see most of the people making mistake here. Rest all everybody knows. This is where usually people go wrong. What is the mistake they make? They are trying to find the current through this. They will only talk about this resistor. Actually, you should be talking about the other resistor. Okay, this is something I see people going wrong. Find this voltage R1 R2 R. Your voltmeter is connected here with plus and minus like this. What is the voltage? It will read. How will you find this? Find this voltage. Find this voltage. Find the difference. See, you can redraw this circuit like this. Find this voltage with respect to the ground. Find this voltage with respect to the ground. V1 with respect to the ground. V2 with respect to the ground. Finally, find out what is V1 minus V2. That is the answer. bridge circuits, they say bridge circuits. Potential divider equation, basic potential divider. What is the basic understanding of voltage source, friends? I have a voltage source, let us say it gives 100 volts, and I connect here 1 ohms. How much current will flow here? 100 amps will flow. I connect one more resistor, 10 ohms. What is the current through this one? Here the current will be 100 divided by 10. 10 amps. Do you talk about this resistance? No. Because voltage across the junctions are same. Here it is 100 volts, so is here it will be 100 volts. You can keep appending or cascading any number of parallel resistances. According to that resistance, current will flow. The same way here, according to this branch, current will flow. According to this branch, current will flow. Now what is this branch? 2R. Sorry. So what is the current through this one? Or what will be the voltage here? Same resistances. 5. So V1 will be 5 volts. If you connect two same resistances, what will be the voltage across this resistance? That's what we are interested in. It will be R, this R divided by total resistance R plus R into 10. That is what is 5. See, we did it some time back. What is the voltage across this resistance? 2 divided by total resistance. The same way here, R divided by total resistance. So it will be 5 volts. How about here? Here it will be 1.1 R divided by R plus 1.1 R into 10. I just want you to understand that when you talk about this branch, this has nothing to do with it. Because a voltage source, the meaning of voltage source is, it is capable of supplying any amount of the current across all the branches to maintain the voltage. See, I gave an example here. To find out this current, we don't talk about this current. This current through this branch will only depend on this resistance. Something very basic, you all know. You can just spend some time. V1 is 5. What is V2?
5.23.
5.23. Okay, then what is V minus V2? Minus 0.238. V2 is 5.238. V1 minus V2 is minus 0.238. This is the option. What is a new thing you should have learned from this one? Voltage across the junctions are same. After you have defined the voltage sources, When you talk about this branch, you don't talk about that branch at all. The basic understanding of voltage source is what? It will give you any amount of current to maintain the voltage. We can take a break for 5 minutes. இருக்கு சார்.
இங்க மைனஸ் போட்டா ஓகே. இங்க எடுக்கிறீங்க, இங்க பிளஸ் பண்றீங்க, இங்க பிளஸ் மைனஸ், இங்க பிளஸ் I1 பண்றீங்க, I2 பண்றீங்க, ரெண்டாவது 16 ரெண்டு ஆட் பண்ண 16 போகணும். டோட்டல் ஈக்குவல் டு 24. அதை விட்டுருங்க, I1 2 தான் வரும். வெளியே போடுங்க, போடுங்க. I1 2 தான் இங்க வர்றதுக்கு இங்க வந்து
Same problem, one small difference. Instead of voltage source, what if you have a current source? What is the voltage here? Same problem, but a voltage current source instead of a voltage source. How do we do? Again, I will redraw the circuit. See if you understand. 10 amps is coming. They say 10 amps is coming. But if I will add these two resistances. What will be the total resistance? 2R. Again, add these two resistances. What is the resistance?
2.1 R.
Now, what is the current through this? What is the current through this? Current division. I reduced the number of resistors, just added them. The more you solve, the easier it becomes. There into the voltage source and current source. Okay. If you know how to solve with voltage source, if you know how to solve with current source, you are done. You are ready for the exam. Voltage means voltage across the junctions are same. Current means current gets divided when there is a branches. There is a junction, current divides, but voltage remains the same. We said that 10 volts will be there across these two junctions, but when it comes here, we say that current is going to divide. So what is the current through 2R? What the current through this will be? The current through this will be 2.1 R divided by 4.1 R into 10. How much is it? 5.12 amps. And what will be the current here? You don't have to calculate. Out of 10, 5.12 is gone here. How much will be left here? 4.88. Current division. Smaller resistance, more current. Greater resistance, less current. Basic stuff. 5 minutes, 10 minutes you spend, you will get it. That's it. Now tell me, now you know the current through this fellow. I want what is the voltage across this one. So that means you know the current. How much is it? 5.12 amps into R. That is the voltage here. What is the voltage here? 4.88 amps into 1.1. So that is the resistance. So V1 will be, what is V1? 5.12 R. That is V1. What is V2? 4.88 into 1.1 R. So how much will that be? 5.368 R. So what is the difference? V1 minus V2? That will be minus 0.248 R. Depends on the R also. See, whatever current flow, current remains the same when it passes through series components. Current remains the same when it passes through the series components. But when it comes to a junction, current divides. Current remains the same when it passes through the series components. Whatever current goes through this, the same current has to go through this. But when it comes to junctions, currents will divide. About voltage, voltage across the junctions are same, but when it comes to series, voltages will divide. All right. I guess you've got some idea here. Next is, let's talk about dependent sources. I think we could explain that with this problem. See, whenever you see this kind of a diamond, it represents dependent source. Circle means it's a independent source. What is the meaning of dependent source? First of all, this is a current source. How do I say it's a current source? Here mark it. So this is a current source. And how much is the current? 2I. That I comes from here. If you say this is 1 amps, this will be 2 amps. A practical application of this is, we will do little bit later. For a BJT, what is the current equation? Beta equal to IC by IB. Yeah. So whatever current goes here, IB decides this IC. So when you try to model a BJT, we try to say like this, that this is the base, this is the emitter, this is the collector. When you try to model a BJT, between base and emitter, there is a IB flowing, let us say. This IB decides this current. This will be beta times IB. See, this current is a dependent on this current. What is a BJT? BJT says whatever current you have to need in the collector depends on what is given on the base. How do you explain it in the circuit world without the transistor diagram? You will explain it with what is called dependent source. This is a current source. That is here you have a current source at the collector, and that current source depends on the input current. So I'm just giving you an application of this dependent source. BJT, MOSFET, there will be some dependent sources. So how about this? You'll have to write a KCL at this node. See if you can write it. Go ahead. Think about it. See if you can solve it. You can think of it like a water pipe. I'll just give you an idea. See if you can solve it. if I current is flowing through this is the same resistance. How much will current will flow here? So let us say this node has a voltage Vx. That Vx, what is the current I? I equal to Vx divided by 4. And what will be the voltage here? Same, Vx. So this will also be I. So what is the total current coming from here? 5 amps, very good. And that 5 amps has to divide by I, and 2I. So totally it is 5 amps, or you can say it is 4I. See, it is understandable. 5 amps is also equal to 4 times I. So what will be I? 4, you can say it is 1.25 amps. So I got I. You can find voltage. What will be the voltage? Tell me what is the V1 and V2. That's all. I've done. I've solved it. Where did I start? I started with trying to see what is the voltage across the 4 ohms. Vx. I know that same voltage will be there across the branches. Now I got current through all the branches. What is Vx? What is this voltage? V1 is also equal to Vx. I have given the equation. So what will be Vx? 4 times I, which is 5 volts. What will be V1? V1 is 5. What is V2? Correct. So how about, I think you have got the answer. What is I? I is 1.25. So Vx is also equal to V1 equal to 4 times I, which is 5 volts. What is V2? So Vx is 5 volts. What is the potential drop across this resistor? What is the potential drop? What is the potential drop across this resistor? 4 into 5, 20 volts. So what is the voltage from here to here? From here to here, 20 plus 5. So it will be V2 will be 20 volts plus 5 volts. 25. Again, few minutes stop. If you have some doubt, I shall explain again. You want me to explain, sir? This one? You want me to explain? You can ask me. We know that 5 amps will start, will go through that 4 ohms. After that only it will divide. 5 amps will start, go through the first 4 ohms, and then it will divide. How will it divide? It will divide as I, 2I. So totally 4 I's it will divide. So from that you know that 1/4 of that 5 amps, which is 1.25 amps, will flow through the 4 ohms. Now you know the potential. Potential will be same across the junctions. So I got V1. What do I mean? I mean this current 5 amps will start from here. This 5 amps will start from here and then it will divide. So here it will be 5 amps. Afterwards it will divide. How will it divide? 1/4 here, 1/4 here, 2/4 here. I, 2I. So I say that 5 amps equal to I plus 2I. There used to be some other option. No? Anyways, whatever current starts from here, it divides here, here, and then here. So 3 divisions. So what is the voltage dropped across this? Because of that, you are going to have plus here, minus there, 4 ohms into 5 amps, 20 volts. Afterwards, you find voltage across one branch, that is sufficient because that is the same voltage across each and every. Then I find here 1.25 amps into 4 ohms, that will be 5 volts. So 20 plus 5, 25. That is the total voltage here. If you try to measure from here to here, you are measuring through this one, it will be 25 volts. All right. So if there are no doubts, I can give you another question. You'll have to find Vx. There are two dependent sources. One is a dependent current source, the other is a dependent voltage source. There is an independent 5 amps current source also. First, find out which are the unknown nodes. How many nodes are there here? How many nodes are there? Node means the junction point. How many junction points are there? What are they, sir? This is one junction point. This is second. That's all. What more is it? Only two junction points are there. Two nodes. One junction point, you can say this is Vx and this will be Vy. Just giving some name. Write a KCL for Vx, write a KCL for Vy. You'll get the answer. All the currents entering the node equal to 0. Name it like that. Go ahead, write a KCL equation. Of course, this Vy we already know. This is a voltage source, no? So you already know what is Vy. What is Vy? 0.25 Vx. So this is a voltage source, no? So you already know the voltage. Of course, dependent. Here there is no voltage source connected. So you don't know the voltage you are trying to find. At Vx, how many branches are there? How many branches are there? Four. Four branches are there. Tell me what is the current through each and every branch? I'm going to write KCL for Vx branch. At node Vx. How will you write? For this branch, how will you write? Vx minus 0 divided by 20. How about this branch? Vx, yeah, Vy is 25 Vx by 10 plus what is 5? 5 amps, yeah. Minus, this is current going out, no? So minus 0.5 Vx equal to, this is current entering, that is current leaving. Now find out Vx from this. That's all, now you got the answer. Maybe I can redraw the circuit just for your interest. Think to redraw, maybe I'm just trying to. 20 ohms is there, 10 ohms is there, 5 amps is there, 0.5 Vx is there. So there are four branches here. This current is entering, this current is leaving. Hey, a small correction. When you say Vx minus 0, what is the direction of the current? Going down or up? So that means the meaning of this is you are saying current is going out. Vx minus Vy means you are saying current is going out. So what this equation will be? Outgoing. What we are writing is every time all the currents leaving the node equal to 0. So this should be minus 5 and plus 0.5. You can always write like that also, but you should be very careful. When you say Vx minus 0, you are saying that current is going out. Because this is greater voltage, no? This is lesser voltage, Vx minus. One variable, one equation, you can get the answer. How to write KCL? What is Vx? For people who did not get it, you can multiply by 20 the whole equation. So it will be 20 Vx. So here it will be 2 times you have to multiply Vx plus 2 times you have to do 2 Vx minus 0.5 Vx, 20 minus 5, 20, 100, 20, 10. So this is the equation. I just multiplied the whole equation by 20 so that there are no denominators. Final answer is 8 volts. More recent question. Find I. 2 marks they have offered. See, all these class of circuits are called bridge circuits. Okay, I'll just give you an idea about bridge circuits, where it is used, how it is used, and then you might see this problem maybe a little bit differently. These are all usually used for measuring. The bridges are used for measuring. There's something called Wheatstone bridge. What is it used for? How does it work? Say if you are trying to use this thermocouple or thermistor to do temperature measurement. For example, if the thermocouple the resistance is 2K, say the room temperature it is 2K. This is thermocouple, or maybe not thermocouple. It's a voltage source. Maybe thermistor, which is a resistor. It's a 2K resistance. what I'll do is I'll put 4, I'll buy 3 2K resistors. Then I'll connect a voltage source here. Now what will be the voltage here? Whatever voltage here will be the same voltage here. So what will be the voltage here? 0. We call it balanced. The bridge is balanced. They say that you multiply these two resistors equal to these two resistors. We call it Wheatstone bridge. Now when this resistance changes, this voltage changes. Based on that, you measure what is the temperature, which is an unbalanced case. Whenever bridge is balanced, what is the voltage here? 0. That's the point to remember. Whenever the bridge is balanced, the voltage here will be 0. Now you see, come back here. What do you see here? Is it a balanced bridge? Is it a symmetric? Resistors are same. If you try to draw a line, the left side resistors are same as right side resistors. It's a balanced bridge, right? Whenever it is a balanced bridge, the voltages here will be same. You take a resistor and correct 100 volt here and 100 same 100 volt here. I say 1K. What is the current through this? Because current depends on the potential difference. When the voltages are same, what is the current through this? 0. And what is the potential drop will also be 0. So that means this is nothing but a short circuit. When the voltages are same, this resistor does not matter at all. It's a short circuit. Now you see the circuit will be different. Where did I start? I started with something called a bridge circuit, Wheatstone bridge. The meaning of Wheatstone bridge is the basic underlying principle of Wheatstone bridge is we try to keep it in a balanced case. Whenever there is an unbalance, there will be a voltage developed, potential difference developed. So we try to, here we see it is balanced. The moment it is balanced, potentials here and here are same. So that means this resistor does not matter. It's a short circuit. If it is a short circuit, now redraw the circuit. How does it look like? These two resistances are parallel. R1, R1. Short circuit. And then the resistor R1 comes. Then R3 comes. Then again another R3 comes. Then again R1 comes. Now again two more resistors, R1, R1. See how simple the circuit is. The point to remember is bridge. There are lots of questions on bridge, whichever department you are from. We solved some time back one question, and this is another question. I can show you some more. In case if it is not a balanced bridge, what do you do? Such a tricky situation. How do you think you can solve this question? You'll have to do delta to star, right? How will you solve this question? If say these resistors are different, this is R1, this is R4, then what do you do? You'll have to do this delta as star, then again maybe this delta to star, try to reduce it. Such a messy business. But in gate they kind of keep it. Most cases, if you are taking more time for a question, that means you are giving a wrong approach. Move on. Don't waste time with it. Okay. So the point is, there are a class of circuits called bridge circuits, which is used for primarily measuring from low frequency to high frequency. And the idea is, if the circuit is symmetric, left side, right side, there is no potential difference developed at all. It's a balanced bridge. And so is this case, balanced bridge. What is the answer? Parallel resistance, sir. R1, R2, R3 values are given. Substitute. If you have two same resistance in parallel, what is the net resistance?
By 2, so divided
By 2. So if it is, what is the net resistance of these two? 0.5. 1, 1. And this will be 0.5. And this will be again 0.5. And this will be 1.5. Again 1.5, 0.5. You'll have to find. Spend time. I think parallel is, this is something you should be able to do.
For parallel and RP only we need to find parallel resistance.
இல்லை சார், இது ரெண்டு பேரலல்னு சொல்லுங்க. அப்புறம் இதுவும் இது ரெண்டும் பேரலல் தானே, 0.5. அப்போ 1.5, 0.5 பேரலல், அது தனியாக பண்ணும். So for people who have lost touch, problem can be solved like this. 2R1 parallel. இங்கே என்ன வரும்? R1 parallel with R1. அது இல்லாமல் it is parallel with R3 parallel with R3. Again R1 parallel with R1. So this is the net impedance. So this can be said as R1 parallel with R1 is 0.5. 0.5, 1.5, 0.5. What is the net resistance for this? What is 0.5 parallel with 1.5? It will be lesser than the smallest number. Always remember, the net resistance should be lesser than the smallest number. What is the smallest number? 0.5. So it will be definitely less than 0.5. If you do parallel to, it will be 0.375, 0.5, 0.5. So this is the total resistance. It is 1.375. Parallel resistances, how do you handle? So is there a formula for parallel resistance? Maybe I am not doing it. What is the formula? How did you get 0.375? R1 into R2 divided by R1 plus R2. So what is the voltage given? 11 volts. So 11 volts divided by net resistance, current will be 8 amps. Final answer is 8 amps. What is the new thing you should have learned through this problem? Wheatstone bridge or bridge circuits. Final answer is 8 amps. Source is 60 volts. What do? Write a simple KCL. Which node is it? I should be writing KCL at this node. That's all. 2 mark question. You just write one KCL, you will get answer. How many branches are there? 3. You can give a name like V1, like that you can give a name V1. Node 1 V1, like that you can give a name. How will you write? What is the equation? V1 minus 60 equal divided by 5 plus. Is it plus or minus? So that's what we had a problem, right? What we are writing is KCL we are writing is current leaving the node we are writing. Why? Because you are saying V1 minus, no. So V1 minus 60 divided by 5 plus V1 minus Vx divided by 3. And what is this one? Minus. And how about a node here? What is this node called? Vx node. Right, for Vx also. This is at node V1. What we are writing here is currents leaving the node equal to 0. Now you'll have to write at node Vx. At node Vx. How will you write at node Vx? Vx minus V1. That means you are writing like this. Vx minus V1 divided by 3 plus Vx minus 0 divided by. Now you've got 2 equations, 2 variables you should be able to solve. If you are from ECE, you can expect around 8 to 10 marks here. If you are from electrical, maybe 5 marks, 5, 6 marks. If you are from instrumentation, again 10 marks. What is the difficulty in scoring marks here? KCL. You know how to write KCL and solve the equations. You know how to do everything. Where you should be careful in KCL. If you are writing all the currents leaving, you should be very careful. So what I would suggest is try to get relation between V1 and Vx here. Substitute Vx here. That's all, you will get V1 and Vx both. See, one other way I could think of solving this is just a hunch. I really don't know if it will work. Let me attempt. Let me give some names here. I1, I2. What is the relation between I1 and I2? This is the current which gets divided into I1, I2, right? So 0.04 Vx is the current which gets divided as I1 plus I2. What is V1? V1 will be I2 into 3 plus Vx. What is Vx? I2 into 5. So I've got these equations. Does it help anyways in solving it, or does it become anyway simpler? And what is this 5 ohms? 5 ohms is 60. No, V1 minus. Yes, V1 minus 60 is I1 into 5. Agreed? With this, can you solve it easier? I'm just saying, I don't want to directly jump into this equation solving. Is there any simpler way? I was just looking. Where did I start? I started saying that this is the current, it gets divided. So I made this equation. And I1 is the current flowing through this resistor after all. So the potential drop on this will be potential difference between these two. So that's how I got this one. V1 minus 60 will be 5 into I1. I guess I got everything right. Is there anything else we need? We are only after all interested in I2. So does it serve the purpose, or is it just extending all these things? So what you could do, you could substitute V1, instead of V1 you could substitute 60 plus 5I1 equal to 3I2 plus 5I2, and that would be 60 equals 8I2 minus 5I1. This is one equation. And the other equation will be I1 plus I2 equal to 5 times I2, right? So it will be 5 4s are 20. 0.2 I2. So it will be I1 plus 0.8 I2 equal to 0. So I've got equation number 1, equation number 2 in terms of I1 and I2. This in terms of potentials, that is in terms of I1 and I2. To solve this, get I2. That's all we are interested in. We are interested in I2, yes. See, this is one way to solve. This is just another way that I just thought of. See, whichever is good for you, think about it. Five amps. I2. How did you solve, sir? Which way? This way.
Both ways.
Both ways you get same. Is there any other way to solve this? Do you think writing a KVL loop equation will be easier anyways? I just did not even think of KVL because there is a dependent source. There is no need for it.
This one
Correct, sir. Correct.
super
5
mesh.
amps. Huh?
Super mesh.
ஓ இந்த லூப் அப்படியே எழுதிட்டீங்க எழுது கரெக்ட் இது பண்ணுங்க சார் அதாவது நேராக கேவிஎல் இந்த லூப்புக்கு எழுதிட்டீங்க அப்படிதானே கரெக்ட் கரெக்ட் வெரி குட் சார் எழுதுங்க
மைனஸ் இந்த வோல்டேஜ் சோர்ஸ் போடும்போது மட்டும் எனக்கு கொஞ்சம் கன்ஃபியூஸ்
சார் சார் ஒரு நிமிஷம் ஆக்சுவலாக கொஷின்லேயே அந்த ஐ2னுடைய டைரக்ஷன் கொடுத்துருக்காங்க நானும் அவங்க வந்து எப்படி கேட்டிருக்காங்கன்னா வாட் இஸ் த கரண்ட் த்ரூ த ரெசிஸ்டர் 3 ohms அப்படிதான் கேட்டிருக்காங்க மேக்னிடியூட் தான் ஸோ பிளஸ் மைனஸ் பத்தி கவலையே இல்லை நாங்க இப்படி எடுத்திருக்கோம் அப்படிதானே நீங்களும் எடுத்திருக்கீங்க ஏன் உங்களுக்கு மைனஸ் வருது இந்த கொஸ்டின்ல மேக்னிடியூட் தான் கேட்டிருக்காங்க அதனால பிளஸ் மைனஸ் பத்தி ஒண்ணும் இல்லை பட் நீங்க போட்டது கரெக்ட் சார் அதாவது என்னன்னா நீங்க இந்த லூப் எடுத்துட்டீங்க அவ்வளவுதான் கரெக்ட் அது கரெக்ட் ஏன்னா இது கரண்ட் சோர்ஸ் ஏற்கனவே அதனால அதை எடுக்க வேண்டியதே இல்லை கரெக்ட் நாங்க போட்டதை பத்தி என்ன நினைக்கிறீங்க? இது இந்த மெத்தட் இப்படி ரைட் சைடில் கன்ஃபியூசிங்.
சூப்பர் மெஷ் வந்து கொஞ்சம்
டேரக்டா லூப் ஈக்குவேஷன்.
டேரக்டா அப்படியே I1 இஸ் ஈக்குவல் இப்படி எடுத்துருங்க சார். I1 + 0.04 Vx இஸ் ஈக்குவல் டு I2 வந்து அது ஒரு ஈக்குவேஷன் வந்துருச்சு சார். செகண்ட் ஈக்குவேஷன் வந்து நம்மளுடைய சூப்பர் மெஷ்ல ஒரு ஈக்குவேஷன் எடுத்துக்கலாம். ரெண்டு ஈக்குவேஷன் கொஞ்சம் இது கொஞ்சம் பெருசா இருக்கு. காலேஜ்ல சொல்லும் போது உங்களுக்கு கரண்ட் தான் கண்டுபிடிக்கணும்னா நெக்ஸ்ட் பக்கம் கொஞ்சம் சீக்கிரமா வந்துடும் அந்த மாதிரி.
கரெக்ட்.
அவங்க தான் சொன்னாங்க.
கரெக்ட் தான் சார், கரெக்ட் தான். இட் இஸ் ஜஸ்ட் மை தாட் ப்ராசஸ். ஐ ஜஸ்ட் டிட் திஸ். நான் என்ன பண்ணியிருக்கேன்னா, நீங்க ஃபுல்லா எழுதிருக்கீங்கல்ல, நான் அதையே ஸ்ப்ளிட் பண்ணி எழுதியிருக்கேன். அவ்வளவுதான். புரியுதுங்களா? நீங்க ஒரே ஈக்குவேஷன் எழுதிருக்கீங்களா பெருசா, நான் அதையே ஸ்ப்ளிட் பண்ணி தனித்தனியா எழுதுனேன்.
அந்த வோல்டேஜ் சோர்ஸ் போடும்போது மட்டும் லைட்டா கன்ஃபியூஷன் இருக்கு.
எந்த வோல்டேஜ் சோர்ஸ்?
இந்த வோல்டேஜ் ஆனா அதனால ப்ளஸ் தான் போற மாதிரி இருக்கு.
இங்க எந்த வோல்டேஜ் இது?
சார் இந்த வோல்டேஜ் நம்ம கரண்ட் இங்க வருது. இந்த ப்ளஸ் போடுறோம் மைனஸ் போடுறோம் லைட்டா கன்ஃபியூஷன்.
கரண்ட் என்ட்ரிங் சைடு ப்ளஸ் சார், அவ்வளவுதான். அது இல்லாம இந்த கொஸ்டின் அவங்க சொல்லவே சொல்லிட்டாங்க, இந்த பக்கம் ப்ளஸ் இந்த பக்கம் மைனஸ். நீங்க Vx என்ற டேர்மை யூஸ் பண்றீங்க அப்படின்னா கண்டிப்பா இதுதான் ப்ளஸ் இதுதான் மைனஸ்.
Vx = டேரக்டா 5.
இது கரெக்ட் தான், இதுல டவுட் இல்லை. நீங்க ஒரே ஈக்குவேஷன் எழுதிருக்கீங்க, நான் பிச்சு பிச்சு எழுதிருக்கேன். Everybody gets the answer? 5? Is it tricky? No? Is it easy? See, this is something that you should do more and more. Okay, so this is no excuse. You have done enough here in the class. Maybe I will do a couple more. But when you go back, you should do more. Because they have no other go. They have to ask you something here only. All right, the final answer is 5 amps. The current through this is 5 amps. They are only interested in the magnitude, so obviously the direction does not matter. Plus 5 minus 5 doesn't matter. Another 2-mark question. See if we can solve this. It's again a 2-mark question. Find current I. They want you to find this current I. The question. சரி, இந்த மாதிரி கிரவுண்டே இல்லாத கொஸ்டின் இப்போ இதில் எங்கே 0 வோல்ட் எங்கன்னு நம்ம சொல்லவே முடியாது இல்லையா? ஸோ யூ கேன் டேக் சம்திங் as 0. Somewhere you have to start, right? Because 0 இல்லைனா you will get stuck. I would suggest this as 0. Which one will you choose as 0? I would suggest this as 0 volts. The reason is For this supply, you can easily say that with respect to this, what is the voltage here? With respect to this, here it will be 8 volts. But here, if you say 0, you cannot really say 8 here because there is a resistor. So for that reason, I would say you can take this as 0 volts. Now you can redraw the circuit if you want, but otherwise you just can go ahead, write KCL for this node. You can say Vx, whatever you want to name it. Yeah, you can write, what else can you write KCL for this? Is there any other node you would like to write KCL? And by the way, of course, you know that here yeah, I think if you say 0 here, here also it should be 0. It's not that only the 0. 0 here also, right? It really does not matter. They just want you to find this current, that's all. 0 everywhere. How many branches are there? What is the voltage drop across this? This is 8 volts. How much current is flowing in the branch? So what is the voltage drop across this?
5 volt.
So if it is current is entering here, because the current direction is like this, no? Current is leaving here. What is the voltage drop? Here it is 8. Then what will be the voltage here with respect to the ground? 5 gone, sir. 3 volts with respect to the ground. I don't know if it matters, I just said. Write a KCL, sir. How will you write KCL at this node? Let us say this is Vx. Vx, I'll start with this branch. Current leaving the node. And one more thing. சார் இந்த மாதிரி மாத்தி எழுதலாமா கரெக்டா தப்பா சீரிஸ்ல இருக்கிற ரெண்டு காம்போனன்ட்டை மாத்திக்கலாமா
and 8 voltage plus the system
சார் சார் we'll think about it. We'll see. Maybe we'll try some other example we'll take and then we'll see if that is okay or not. Maybe I'll take an example and then try. And same thing. Say I have a 10 volts here. 2 ohms. 8 ohms. 1 ohm. One then. Another is 10 volts. Do you think these two circuits are same? Yes, no. Sir? சேம் வோல்டேஜ் சார், எந்த வோல்டேஜும் மாற்றல, நான் பொசிஷன்ஸ் ஆஃப் த ரெசிஸ்டர்ஸ் தான் மாற்றிருக்கேன். இல்லை இல்லை, சம் நியூ சம் வாட் ஐம் ஜஸ்ட் ட்ரைங் டு அண்டர்ஸ்டாண்ட். இந்த மாதிரி நீங்க காம்பனன்ட்ஸ் ஸ்வாப் பண்றது அலௌடா இல்லையான்ட்டு. சீரீஸ்ல இருக்கிற ரெண்டு காம்பனன்ட்ஸ் ஸ்வாப் பண்ணலாமா பண்ணக்கூடாது. I just took a situation where 8 volts is at the top, 1 ohms is on the bottom, and the other case is 1 ohms on the top, 8 volts on the bottom. Do you think they both will give the same results? Let's write KVL. No, how do you do it? Let's write KVL. Use another color. See, this will be helpful to us, right? Minus to plus, plus to minus, plus to minus, plus to minus. So what will it be? 10 volts minus 2 into I. I don't know what that I is. And then what do you say about this? Minus 8. And here it will be minus I equal to 0. How do you say here? Is there any difference? No, right? So KVL says you can do it. KVL says you can do it. Commutative. So commutative. Mathematically, it's called commutative, right? So you can do it. So that means when you change this, then KCL becomes much easier, right? This is how will you write KCL for this? How will you write? Maybe I'll rub this off a little bit. Vx minus 0 divided by 1. Vx minus 8 divided by 1. Vx minus 8 divided by 1 plus Vx minus 0 divided by 1 equal to 0. Find Vx here. How much will it be? Vx is 2, right? 2 volts. Now I know Vx, 2 volts. For Vx, no, it's 16. 4, sorry. 4 volts. Now you know this voltage. You know current through each and every branch. What is the current through each and every branch, if you can tell me? See, after all, current through this is what? 1 amps is coming. What is the current through this one? 4 amps. Here the current is, no sir, 4 volt minus 8 volts. This is 4. This is 8. So it will be, I think current will be this direction. So how much will it be? 4 amps. But the direction will be like this, 4 amps. And how about here? 4 amps in this direction. So, and how about here? So here it is not there. So here it will be 4 and 4 coming in, 4 and 4 going out. So the current here will be 4 amps coming, goes inside. And sorry, madam. This one. I'm stuck here. See if someone can help me. what is the problem here? I want to find this current. Yeah. How did you do, sir?
2 amps.
Oh yeah, you did loops. We'll do loops. I know there are how many equations you got? 4 equations.
I1
Yeah, this is source.
directly we can.
Yeah, we'll do it. That is always there. So you can always write loop equations, 4 loop equations. That is something we'll do. I just trying if there is any other simpler way to do. KVL we can do for loop equations you can do. If it works, we'll see. Otherwise, we'll go back to that. I think that's about it. Sorry? சரி இது 1 amp தானே இது 1 amp 1 amp comes 4 amp. See, this is 1 amp, this is 4 amps. Obviously this has to be 5 amps. இங்க 4 amps இதுல போயிடுச்சு, இதுல 1 amps. இதுதான் ஆன்சர். பார்க்கலாம். 57. Hey, -1. Yeah, correct. Looks -1 amps. உங்களுக்கு என்ன வந்தது? Looks like we are better. இதுல எவ்வளவு சார் இருக்கும்? எப்படி சொல்றீங்க? ஓயா, இது ரெண்டும் சேர்ந்து இதுல 5 amps போய் என்ன 5 amps போய் 4 இதுல வந்துச்சு, 1 இங்க போயிடுச்சு. ஓ யா, இட் சாட்டிஸ்ஃபைஸ் எவ்ரிதிங். How do we explain for people who did not get it? Where did we start? We started with simple KCL equation. To write this KCL equation, the first observation is we had this problem of a resistance and a voltage. So we kind of made sure with KVL that yeah, you can replace them. It really does not matter. If they are in series and there are no branching tapping out in the middle, you can definitely replace them. After you replace them, it looks much more simpler. It looks like 8 minus Vx and 8 minus Vx, 0 minus Vx, 0 minus Vx. So it looks a very simpler equation. And then we get Vx voltage. And then it is just, after all, just finding out the currents through each branch and satisfying the whole system. If the whole system is satisfied with the current numbers, you have got current through each branch. Maybe I can write with a fresh page. What we did is this: 8 volts is there. We had 1 ohm, 1 ohm here, and 1 ohm here. And we already said that some 1 amp current is flowing through this. Some resistance is there. All that we made, what made difference is this one. So this is the situation. We wrote KCL for this node. How do you write KCL for this node? 8 minus Vx, or maybe Vx minus 8 divided by 1 plus this branch, Vx by 1 plus this branch, Vx by 1 plus this branch, Vx minus 8 divided by 1. From this we find Vx equal to 4 volts. So until then, until this, it looks like it's straightforward. Now once you have got this 4 volts, we try to find current through each branch. Current here will be 4 amps, but in this case the current will be here greater voltage, lesser voltage, right? So 4 amps here, and again current here will be 4, and here again, because greater voltage, lesser voltage. So this is what makes the difference. Now we try to satisfy the system. What do we do for that? If 1 amps is coming here, 4 amps is coming here, obviously what is the current here? 5. And out of this 5, 4 is going here. So what is left? 1. And then obviously these two things will join, and what will be here? So this is like a satisfied system. This is what we did. You can write loop equation. I don't know if you try to write a loop equation, what you will end up in. I don't know. Should we try that loop equation thing, KVL? We could try, right? KVL. Why don't you write 4 loop equation, I1, I2, I3, I4? Let us see if that one works. We will learn something there. Okay. Maybe that loop thing you can try during lunchtime. There is, after lunch we'll attempt it. I just want to attempt one more question before lunch. Simple bridge question. All right. Just one last question will break. So this is again 2011, 2-mark question. Current source, it's a AC source. There is some printing mistake. Fine. Friends, this is not ampere, it's volts. Find I. That's all. Find I. That's all is given. It's a 2-mark question. See, if you have a voltage source, if you want to find the current out of it, you have to reduce the impedance. You have to reduce that whole impedance. How will you reduce the impedance to a single impedance value? Very good. There is a delta there, no, at the bottom. Convert it to star. It will become a smaller number. There is a delta at the bottom. 3 6-ohm resistors are there. Convert it to star. What is the current, sir? Friends, this is a test for your complex number understanding. If you know how to handle complex numbers, you can do it easily. Okay. If you have a delta with all same resistors R, what is the star divided by? Always remember this, friends. It will save a lot of time. I already told you that the star network will be smaller resistors than the delta resistors. How small will it be? If it is all same, it will be 1/3. For example, if they give 111 here, it will be, so here 111, if they give, it will be 333. Okay. So just remember this, it kind of saves a lot of time. You don't have to every time go back into that equations. So how will this become? 2 amps, correct. So this will become J4 2 ohms minus J4 2 ohms, and how this will be again 2. So this is the total impedance. So 2 plus J4, 2 minus J4. How will you handle them in complex numbers? Make them a single number, single impedance, add it to the 2. So this will be 5 ohms. Okay. So this is something that you should know how to do. So net resistance is 7 ohms. How do you do this parallel impedances? Complex numbers.
1 by 2 plus 4j.
Correct, sir.
Plus
Correct.
1 by
So this
2
will
by
be
4j.
1 by R. That is this. Maybe I should use Z. The net impedance will be 1 by 2 plus 4j, J4 R maybe, plus 1 by 2 minus 4. So this is something, a complex number thing. I want you to go look into it. Complex number basic. If you have idea, good. I'm happy about it. You can just cross multiply, do something like that, right? For the interest of people who are who don't know complex numbers, how do you solve this one? The denominator will become multiply. A plus b into a minus b will be a square minus b square, minus and the j will become plus, so it will become, and the numerator will be so you will end up getting z equal to 20 by 4. How to handle complex numbers? When you have a plus ib into a minus ib, after multiplication you end up getting a square minus I square b square. What is I square? Minus 1. So it will be a square plus b square. Complex numbers. Final answer is 14 divided by 7. 14 divided by 7, it will be 2 amps. The current is 2 amps. I square is minus 1. All right. So just a small revisit, whatever we did. We started saying that RLC, all these three are linear components, linear passive. This is what we started saying. And we said that from the viewpoint of V and Q, R is a first order system, and L is a, and C is a, how does it matter whether it is 0, first, second? Response. 0 is going to an instant response, first is going to give a delayed response, second can be anything. So depending on the differential equation. And then after this, Yeah, this is something we discussed. A capacitor with a voltage source, capacitor with a current source. You see, straight line, integral equation. And this happens again with the inductor for a voltage source. Okay. And then KCL, we saw lots of problems, and it is very likely that we will make a mistake. Here also we made a mistake. What is the mistake? When currents are entering, you should be writing 1 volt minus Vx. So this is wrong, right? You should go back, correct it. What is the mistake? So we made a mistake. The mistake is when you say currents are coming in, you should be saying 1 volt minus Vx, 2 volt minus Vx, 3 volt minus Vx. So that's the mistake we made. I want you to be careful with that. If there are no currents in the branches, right, it's easy, you can escape. If they give one current source, we'll get locked. So KVL thing, you can do it. Start to delta, delta to star. We can do these things. Current division. And then voltage division. Usual mistake, current division means when you're trying to find current through this branch, this impedance matters. But when it comes to voltage division, you're trying to find this voltage, only this impedance matters. And then bridge circuits. Whenever the bridge is balanced, you are going to get 0 volts. Here it is unbalanced bridge. So you are going to get some voltage. We use KCL here. Dependent sources. How do you handle dependent sources? Another problem on dependent source. A balanced bridge. Use that idea. And this one, I just wrote, took this voltage current source, divided, then what is the impedance here? I did that way. And this is one other problem that we did. Okay, we'll catch up after lunch. Come back after an hour.